Hello everyone. In today's video, we will learn how we can solve machine language translation problem, NER problem, and to solve such kind of problems, we have a one architecture called sequence to sequence model, where we have the one section where we like put all those input or target language sentence, and in output we'll get the translation of that. So this is called encoder part, and this is called decoder part. Now, how we can feed this sentence? He is doing good, and the translation of this, which is वह अच्छा कर रहा है. So we need LSTM cell for that, which takes hidden state called HTCT, and the current word as an input, which is here he. Will pass this, and so text directly doesn't go into the machine learning algorithm or deep learning model. We need to convert into some numeric format. So what we can do, we use one hot encoding. So in the total vocab, we have 4 tokens here. He is doing and good. We can assign some numbers to this. This can be our 1, 2, 3, 4. Now this is ultimately the first bit will be active, the others 3 will be 0. Again, this is the first time stamp, so we call it T1. Whatever the output of hidden states we get from here, which is HTCT, which again goes to the different time step. It's a so this encoder, what I'm drawing here, is ultimately one LSTM unit. I'm talking about different timestamp, so don't think it is a different LSTM cell. It's a part of one LSTM cell which I'm drawing. It's a timestamp I'm showing the difference. So in different timestamp T1, T2, different tokens will be going. Like for example, the first timestamp we are sending, now it will send the his. For this, this one hot vector will be 0, 1, 0, 0. Again we'll get some hidden vectors, which are HTCT, goes to the next timestamp. Here will pass the word called doing, which is 0, 0, 1, 0. We get the hidden state output HTCT, which goes to the next timestamp of LSTM cell, T4, T3. Here this word called good will be goes, and the input vector for this is 0, 0, 0, 1. That's good. The fourth number vocabulary word is good, so it will be 1, others will be 0. Now at the end we're going to get this context vector, with just essence of what we have read in the encoder side. Fine, this is the encoder side. Now this context vector, which are essentially HTCT, will go into the decoder part. Now in the decoder there is some different things will be having. So let's tokenize the let's get all the vocabulary present in our training examples. वह अच्छा कर रहा है. There are 5 tokens. So let's write those tokens. वह रहा है. let's remove this one. So we call it 1, 2nd, 3rd, 4th, 5th, and there is another one which are special tokens, which is a start. So how the translation of the particular target language starts with the start keyword, which is special token, and it will end with the keyword called special token called end, END. Okay, so accordingly it will change as well. Let me just remove these numbers. So this is called 1. Sorry for my bad handwriting. This is called 1, 2, 3, 4, 5, 6, 7. There are total 7 vocabulary word here. Now we'll draw the decoder part. So the first LSTM cell, the LSTM cell in the timestamp T1 will be having keyword token called start, and the encoder representation, the vector representation of this word start is just a 1, 0, 0, 0, 0, 0. There would be 6 zeros, so 5, 6, there is an extra 1 0 plus 7 numbers are there, out of which the first is 1, others 6, all 6 are 0. This outputs HTCT, and also outputs the output of this, which is in this case some guess, which is what will come after a start of this start keyword, start token. So it can be any token which is present in our Y vocabulary. It can be वह अच्छा कर रहा है, or and anything can come out as an output of this. So we are assuming that we will be getting the right word, which is वह, or it can be any word, because we are randomly initialize our weight matrix, which are the learning weights, which in this case is W, can be any random number, right? So it can be anything which outputs here. It passed to the softmax function, where we get the different probabilities of each word. So for example, let me draw here. Okay, so there are total 7 outputs, possible outputs, right? 1, 2, 3, 4, 5, 6, 7, 4, 8, 7. Let's remove this one. Yeah. So let's suppose we got 0.1, 0.2, 0.3, 0.1 again, 0.3 or 0.5 and 0.1. It adds to the 1. So considering this is the 0.5, which is the higher number, so in this case it's second last, which is high. This keyword will be coming because this is the location of that. But in the training sentence it needs to be वह अच्छा कर रहा है, right? है doesn't come as a first word, second word after a start. So in the next timestamp, logically we should pass this है, right? This one, the output of this one. But we are not going to pass that one, because in the training phase we need to pass the correct word, which is in this case the वह word, right? This is called वह. So here this vector will be passed, which is in this case 0, 1, 0, 0, 0, 0, extra 0. So there are 7 total positions, and the second one is active, which is this second one where. So we are not passing what we found in the first timestamp. We are passing what needs to be passed, which is in this case where, right? This is called teacher forcing. Teacher forcing. This phenomena is called teacher forcing. Okay, let's go to the next timestamp. So we will be having the word called acha. Same thing, it passed to the here. Now whatever output comes, let's suppose this time we got where, that particular index has highest softmax function value. So this is passed to the next timestamp, and at the end we will be having timestamp which is as an input called word called end, right? So sorry, before that we will be having this word called hai. My bad. So it will be hai, the last word, which is this one, and the vector for this one is 0 0 0 0 0 0 1 1 0, sorry, 4 5 6 is another 0. So last second bit will be active, which is 6th one, and others are will be 0, which outputs the word called end. Okay, so this is the iterations for the training, doing the training, and once it is completed, we'll have second thing, which is where we backprop. So this is the forward propagation. Now we'll doing the back propagation. In the back propagation, two things will be happen. First, back propagation. So first is gradient calculation. Second is update parameter. So gradient calculation is just nothing but getting like differential equation, differentiation with respect to trainable parameter, which is in our case was W, right? We discussed about it, because this is the matrix we have to update, which is the weight matrix. So this is the gradient will give us the slope of our training phase. Accordingly, we'll update those weight matrices, and it only happens once we backprop, we adjust our errors. So in this case we got as a output, but it was not correct. This should be y. So we'll update the weights accordingly to adjust that. So for that we need to require a loss function. So the picture comes for the loss function. So this gradient differentiation always applicable on this loss function. This loss function needs to be the differentiate with respect to dw, right? Now what is this loss function? This loss function is just nothing but categorical cross entropy. So for each word we will checking this, and we will having the y true, which is the actual prediction, and the log of y pred, which is our prediction. This needs to be calculated, and it needs to be sum up or average. Whatever you want to do, you can do. Let's suppose we perform the sum up, and the final loss function we need to update, and we get new like adjusted value of . adjusted value of w, which will update into the update parameter in the second step. This is the second step. In the backprop, this is the second where we update this updated value of w. We keep doing this for different batches, and finally we'll get the good value of trainable parameter w, which is our final destination for training any sequence to sequence algorithm. So I guess you have got some understanding how we can train a sequence to sequence model using LSTM cell. Thanks for watching the video.